Students, welcome to the channel Notion of Mathematics. In today's video I will be discussing that what is the meaning and purpose of Cayley-Hamilton theorem. So for that particular aspect, first of all I will be discussing what is the statement of Cayley-Hamilton theorem. So it is like for any square matrix A, the matrix satisfies its own characteristic equation, right? And a matrix I have taken, it is a 2 by 2 matrix. It is a 2 by 2 matrix. So basically I want to prove here that this particular matrix will satisfy its own characteristic equation, right? So this is the whole process of this. So since this particular matrix have to satisfy its own characteristic equation, so first of all let me tell you what is the meaning of characteristic equation. What is the meaning of characteristic equation? Right? What is the meaning of characteristic equation? So first of all, what is the characteristic equation? That is determinant of a minus lambda I is equal to 0, right? So if as per this particular statement, if there is any square matrix that must satisfy its own characteristic equation, so this thing we have to verify. Suppose this is equation asterisk, right? So I will be evaluating first of all a minus lambda I, right? Where a is what? A is a 2 by 2 square matrix, lambda is any scalar, right? Lambda is any scalar. We say it is eigenvalue as well, and I is the identity matrix. So what it will be? It will be 2 minus 1 minus 1 2 minus lambda into identity matrix 1 0 0 1, or it will be what? It will be 2 minus 1 minus 1 2, and minus it will be what? Lambda 0 0 and lambda. Ultimately what we will be getting here, it will be like, it is just a subtraction of two matrices. So it will be 2 minus lambda minus 1 minus 1, and it is again 2 minus lambda. So it is a minus lambda I. Now thereafter, from this a minus lambda I will be getting here determinant a minus lambda I. So if it is a matrix, so what will be its determinant? It will be just like determinant of these entries. So it will be 2 minus lambda minus 1 and again 2 minus lambda. Now I will be writing here the characteristic equation, and characteristic equation is what? Determinant of a minus lambda I is equal to 0. So I mean to say it is determinant of 2 minus lambda minus 1 2 minus lambda, it is equal to 0. And it is very simple. Now we have to just evaluate and equate, I mean to say, first of all we will evaluate this determinant, and it is already equal to 0. So it will be what? It will be 2 minus lambda whole square and minus 1 equal to 0, or it is 4 minus 4 lambda plus lambda square minus 1 equal to 0, or it is lambda square minus 4 lambda plus 3 equal to 0. Now we have to factorize. Okay, there is no need to factorize it. In this particular proof. There is no need to factorize it. So here is one, I mean to say, this particular equation we have obtained. So the thing is like, I am saying, if this is the characteristic equation, characteristic equation of matrix A, then matrix A must satisfy this particular equation. Okay, now this is the characteristic equation I am saying. So this matrix must satisfy this characteristic equation, right? Its own characteristic equation. As per the statement, every square matrix satisfies its own characteristic equation, right? So this is the updated form of the characteristic equation, this is the modified form of the characteristic equation. So how I can prove it, how I can verify it? So this is the characteristic equation, updated characteristic equation, lambda square minus 4 lambda plus 3 equal to 0. And I am saying that as per Cayley-Hamilton theorem, this particular matrix is satisfying its own characteristic equation. So what I have to prove? I have to prove that a square minus 4a plus 3 into identity matrix is equal to null matrix, right? Okay students, so I have taken the LHS here. LHS is like a square minus 4a plus 3i. So what I have to do, I will be putting the value of a here. So what is the value of matrix A? That is 2 minus 1 minus 1 2. So let me put it here. It is 2 minus 1 minus 1 2 into again the multiplication by same matrix 2 minus 1 minus 1 2, and minus 4 into a is again 2 minus 1 minus 1 2, and plus 3 into identity matrix is 1 0 0 and 1. Now what I have to do, I have to solve this particular expression. So it will be what? Let me multiply these two matrices. It will be 2 into 2 4, and minus 1 into minus 1 means plus 1, right? And here it will be first row and second column, that will be minus 2 and minus 2. This second row and first column, that will be minus 2 minus 2. The second row and second column, that will be 1 plus 4, right? And minus it will be thus multiplication of this 4 with this matrix. So it will be 8 minus 4 and 8, and plus it is like multiplying this with this matrix. So it is 3 0 0 and 3. So ultimately few more updations are required here, that is 5 minus 4 5, that is here 8 minus 4 8, and here it is 3 0 0 and 3. So ultimately all 2 by 2 matrices are here, so we can easily update it like this: 5 minus 8 plus 3, that is 5 minus 8 plus 3. It is minus 4 plus 4 plus 0, it is minus 4 plus 4 plus 0. It is minus 4 plus 4 plus 0, it is minus 4 plus 4 plus 0. It is 5 minus 8 plus 3, it is 5 minus 8 plus 3. So what will be its final answer? It will be 0 0 0, it is 0 actually, 0 and 0. So ultimately what we have obtained here, we have obtained here the null matrix, 2 by 2 null matrix, and that was our actual aim. So in such a way we can say that every square matrix will satisfy its own characteristic equation. So I think student, today's video will be very helpful for all of you to understand the concept of Cayley-Hamilton theorem. For more updates like this, you may subscribe the channel Notion of Mathematics.